I am Pushpita Chanda. I am a PhD student at IIT Delhi under IIT Delhi and University of Queensland PhD program. I am the TA for this course, an introduction to lasers and laser systems. And let us start for today's tutorial, which is for week 8. So, we will discuss fiber laser and semiconductor laser in this tutorial. Since most of the questions in the quizzes for this course is a theoretical based, I'll suggest that you focus on basic theoretical understanding, clear understanding of all the laser working. And yes, there are some other numerical questions, and I have discussed time to time them. So the ability of an optical fiber to keep the light confined within its core and the large accepted angle for the entry of light through its ends are the key to the emergence of fiber lasers as the leader in industrial, medical, and directed energy application. As I have already discussed that the fiber laser basically work on the principle of total internal reflection, and that enables it to keep the light confined within its core. So that is how we use fiber laser. And the fiber laser is basically the leader in industrial, medical, and energy application today. So let's consider a ray. Sorry, this rare denser medium, and this is rare medium. So light ray on the rarer, when the light shines on a rarer medium from a denser medium, the rays that is incident at an angle called theta c passes by the interface of two medium. And as we know that when light goes from denser to rarer medium, it moves away from the normal. So this is the critical angle. When the light falls on the critical angle, it some portion of it is reflected and stay in that medium, and some portion got reflected at the level of the interface. But if a light incident at the angle lesser than theta c, some of it will reflect and some of it will refract. That's a normal phenomenon. Call it C dash dash. But if a ray that falls greater than an angle of theta c, which is this, every energy, all of the energy it lies in the denser medium itself. So at that angle, reflection will happen, and also the refraction will happen at that angle. So that is why it is called total internal reflection. We may conclude that the lights between the B, which falls at an angle, critical angle theta c, and the interface OO dash, all the light will go through the total internal reflection, and they does not lose energy through diffraction and exhibit complete reflection. So for fiber laser to work, actually all the fiber works on this principle of total internal reflection. By the virtue of this total internal reflection, light gets confined within the fiber. This is the typical diagram of a fiber. So it consists of internal glass core and a cladding of a lower reflective index. So cladding has lower reflective index of 4. Here refractive index is denoted by mu, and the core surrounds the cladding. The acceptance angle theta critical or theta accepted is the maximum angle that an incident beam of a light can be imagined to be subtending at the fiber axis in order to able to trap inside the core. So if the light come outside of the theta angle, they will not go through the total internal reflection, and at each interface they will lose some energy, and at the end that part of light will not propagate through the fiber. And the angle solution is theta accepted sin inverse 1 by mu naught root over mu 4 whole square minus mu clad whole square. As it can be seen in the figure that the ray A, which makes the lower boundary of the incident light beam, after its refraction into the core, strikes the interface of the first there will be a refraction, and that after that it's refracts into the core, strikes the interface of the core and cladding at a critical angle, which is the critical angle basically. And the ray which come from this, so that will strike here, and all the ray between the upper boundary and lower boundary, they strike at angle less than critical angle. And this is the 2D representation inside the fiber probe. So actually the light from a 3D core. And inside the 3D volume, every light falls on the end of the fiber. It will be favorable by the total internal reflection of at each interface, and basically it will be communicated or to the other end of the fiber. Uh, so here you can see that B, which is away from the A, although it entered the fiber core, it will not sustain its whole energy uh, throughout the core. That at each interface, it will lose some energy due to refraction. So guided by this judiciously cladded structure, the input bound beam travels down the fiber core and energetically excites the light-emitting molecules doped in the pure glass core of the fiber. A fraction of these photons is spontaneously emitted by these excited dopant molecules, which is present in the fiber core, uh, strike the core-clad interface at angles exceeding theta c and will be trapped and guided in the core as elaborated. These spontaneous photons understandably perform the role of seed photons for simulated emission and can result in the amplification of light with appropriate cavity feedback. However, before gaining deeper insight into the working of a typical fiber laser, we should familiarize ourselves with the basic spectroscopy, because each active species, the laser works because of the fiber laser works, that the fiber works like this, but fiber laser works because of the active species, and they have they work as a seed of simulated photons because of this spectroscopy. The operation of both the fiber laser and the fiber amplifier, the optical fiber functions as a passive element that does not produce light. So you always need to remember that fiber is a passive element. They perform the role of a glass host into which the light producing active medium are embedded, just like the conventional solid state laser. But unlike the laser for which for solid state laser, the most common dopant is neodymium, which for solid state laser, the most common dopant is basically neodymium, which is light at 1.06 micrometer. But for fiber laser, uh, the most common dopant is basically iridium. So this is for both CW and pulse operation, and they are tunable basically. Tunable as well. Low 1.02 to 1.12 micrometer. Although the very first fiber laser made use of neodymium molecule as its active medium, but this has not gained popularity because of the reason that neodymium solid state laser was already producing coherent light at 1.06 micrometer, and they are being used in many industrial and scientific applications. The other dopants for fiber laser this is like erbium, then thulium, then holmium. So the erbium doped fiber laser produce 1.5 and 2.9 micrometer of light. Thulium is about 1.47 and 1.8 micrometer of light. Holmium is 2.1 and 2.9 micrometer of light. While erbium doped laser lag behind the yttrium doped one in power producing capability, erbium doped fiber amplifiers on the other end have revolutionized the way in which the information is transmitted globally. Thulium and holmium doped lasers with wavelengths much longer than 1.4 micrometer fall into ISAFE region of optical wavelength and are of interest owing to their potential in many military and industrial applications. So all these dopants, erbium, thulium, holmium, and yttrium has same kind of electronic structure, and they are similar. But hence, we know that yttrium is being used mostly as a dopant in the fiber lasers. So we will discuss that. First, the spectroscopy is also important in the case of fiber laser. So even though we are discussing the spectroscopy of yttrium doped fiber laser, the spectroscopy of erbium, holmium, thulium based fiber laser is of the same thing. So these are the energy levels. They participate in the lasing action. The both excited and ground state energy levels are split into multiple closely spaced sublevel due to Stark effect because of the interaction between electrons and the electric field present within the solids. So here basically when we pump the fiber laser, there are two strong absorption peak, that is 915 nanometer and 917 nanometer, and a weak absorption peak of 860 nanometer. So they populated the upper different Stark levels of excited state, and majority of the population excited to any of the upper state sublevels relax non-radiatively through the multiphonon decay, eventually to the lower Stark level, which is this. And from this, they emit the light and the transition between from lower level excited start level to the different start level of the ground state result in the lasing level, that is 1140, 1190 and 1035 nanometer. For 1140, in 1090 and 1035 nanometer, we can see that these start levels are not that populated. So from here, there, they also decay to the lowest level of the lowest start level of the ground state non-radiatively. So for these nanometers, these fiber laser work as a 4-level laser. But for 970 nanometer, the transition is between the lowest level of excited stark level to the lowest level of the lowest level of excited stark sublevel to the lowest level of the ground state stark level, and the lowest level of the ground state star level is enough populated. So for 975 nanometer lasing action, the same laser is a 3-level laser. Okay, so the major consequence for the stark splitting is where stark consequence of stark effect splitting is the occurrence of gain and interlacing across a wide range of wavelength. And now we'll discuss the pumping of the fiber laser. Like any other laser, fiber laser is also needs pumping, and it's being done by optically. So in 1961, when first fiber laser was there, side pumping method was used. And due to this, the lasers were unsuitable, like their long strand-like shape. The laser were unsuitable for pumping through the side because of their long. So the scientists moved from side pumping to the end pumping. But the difficulty of coupling the divergent light emitted by a conventional source through the minuscule end of the fiber is responsible for putting any serious research on fiber lasers on hold between 1960 to 1970 for almost a decade. The advent of heterojunction diode lasers, when they are in the market in 1980, the end pumping of fiber laser was possible, and that enabled the scientist to use it for in pumping of the fiber laser. There is and after that there is no stoppage in the research of the fiber lasers for various application impacting humankind. So, as we know in the fiber that the light must enter the core of the fiber within its acceptance angle, a requirement impossible to meet by the conventional lamps and LEDs. So the pump also need to be very strong and coherent. For conventional light source and LED, even some rays would have entered the fiber, but they will not be able to achieve the strength of pumping. So then when the heterojunction diode lasers come into the picture, then fiber pumping for the fiber laser from the end was possible. So the diode lasers emit from a tiny area into a much narrower angle that can effectively transport it into fiber core through its end. The pump light, as we know, will be guided through the length of the core by the phenomena of the total internal reflection. So any light which end in the acceptance angle 3D region, that will be guided through by total internal reflection. For a diode laser of appropriate wavelength, the light will be gradually absorbed by the doped molecules as it travels down the fiber. Just like the ytterbium can be pumped by the diode laser operating around 1950 and 1975 nanometer. Here we can see that these are the absorption peak of the ytterbium. Once a fiber has been active by inverting population, it can perform as an amplifier. However, like any other laser, the onset of lasing is an active fiber requires a cavity. A very simple fiber laser cavity configuration is like this, that if we don't use a cavity, that's a fiber amplifier. But when for a laser, we introduce the cavity, and the diode pump light with the help of dichroic mirror has been used for the pumping, in pumping, and the both of the system reside between two mirrors. The red portion of the fiber is the core, and the black is cladding basically, and the light like optical pumping light travel like this, and in the path they activate the dopant, which is ytterbium most of the time. And we will use diode lighting, which every 975 nanometer and 950 nanometer. The emission from the diode laser is appropriately focused and then launched into fiber by means of suitably located dichroic mirrors that offer high reflection at the pump wavelength and high transmission at the lasing wavelength. That is the basic thing we all know. High transmission for lasing wavelength. The pump and laser beams are indicated in the green and red line. So this is the pump beam and the red is the basically laser beam. And lasing always occur at the longer wavelength of the pump. You can see here. And cavity is formed by that high reflectivity rear mirror and moderately reflective output coupler. The central circular twist on the fiber seen in the figure basically emphasizes the active length here usually far exceeds the cavity length. So basically fiber can be centrally circulated, and for that we append the fiber. There are some guide of using fiber length stitch, but there is some guideline how we can coil a long fiber into a small piece and all. So it's just a visual representation that there are more length than the actual thing. So the long fiber is therefore coiled so that it fit a conventionally sized enclosure. The ends of the fiber are anti-reflection coated to avoid intercavity loss through Fresnel's reflection. The optical cavity formed with such external mirror is, however, quite prone to becoming misaligned due to the occurrence of thermal changes or the presence of physical bumps in the fiber that are inevitable. So, as I say, there is to how to handle the fiber. You know, the thermal changes. Causes physical This alignment problem can be overcome by fabricating appropriate Bragg mirrors inside the optical fiber as the two ends, quite akin to the uses of Bragg reflectors in the operation of vertical cavity surface emitting diode layers. And by using Bragg mirrors, fiber lasers can be misalignment proof. Now, we have to scale up the fiber laser. So by any laser, fiber laser can be scaled up by increasing active length. Basically, that's the easiest way to scale up the the power. But if we do it in the fiber laser, yeah, but some non-linear process became operative and eat away the intercavity power. For fiber, this will cause intracavity power. As we know, the very long and thin geometry of fiber has granted this laser two major advantages: easy removal of waste heat and the built capability to operate on a lowest order transverse mode, that is TE00 mode. So fiber lasers advantages are basically easy removal of. So you need to remember what is the advantages and disadvantages of each laser. And operate on the lowest order transverse mode, which is TE00 mode. However, as the fiber has a very long, narrow core and increase in power also greatly arises the intra-core optical power density in turn associate increase in associated electric field. With increasing power, the field can reach values high enough to set in various nonlinear processes that basically convert laser light into other wavelengths. Thus, any attempt, so the nonlinear processes, the nonlinear nonlinear processes arise different frequency. So we don't want that. We want the frequency we need. So we cannot increase active length there. So it will be counterproductive basically. The remedy will be to put a check on the occurrence of nonlinear phenomena by reducing intercavity power density. This can be readily achieved by raising the diameter of the core, although at the expense of the spatial quality of the laser beam, as a wider core will support higher order transverse beams. The obvious question that arises here is whether the higher order modes can be suppressed in a wide aperture fiber laser to preserve the spatial quality of its emission. So we will increase the diameter solution increase diameter of the pore that can support higher order that support higher order transverse modes. But at the expense of spatial quality. So the popular technique to do that has been to exploit the bending loss of a fiber to an advantage and subdue the higher order modes. As we know, light passes through the straight core without any splittage because it shines on a cladding core interference at an angle greater than the critical angle. However, when the fiber is bent, a part of light will inevitably strike the interference at like the angle lower than the critical angle and will escape as it travels down the core. Like somewhere here, they will not fall at an angle of 5. This situation is like this. The 90-degree complement phi to the angle of incidence theta always increases as the light ray travels from the straight to beam region. So here they were traveling phi 1, but now when the brain region reaches, they will be at phi 1 dash. And wave B travels with a more smaller angle than phi 1 at so phi 2. So phi 2 is smaller than phi. Both these rays travel down the fiber, and as the fiber bends, they respectively now intersect the interface at angles phi 1 dash and phi 2 dash, which is again the greater than phi 1 and phi 2. So as phi is a complementary angle of theta, the angle of incidence is equivalent of saying that the angle of incidence of a ray always decreases as it travels from the straight to the bent portion. In the ray optics description, a higher order mode can be visualized as light rays traveling close to theta c, the critical angle of incidence. While in the case of TM00 mode, the rays are always incident at an angle much higher than theta c. Thus says A and B essentially signifies the higher order and the TM00 modes respectively. It is therefore very likely that a part of light belonging to a higher order mode will leak out through the bent surface. They will leak out from this bent surface and the fiber, and most likely that such a phenomenon will occur for the TE00 mode. Clearly, therefore, a higher order mode will experience greater bending loss than the lower order mode. The sharper the bending is, the greater the loss will be. By judiciously selection of the sharpness of the bend, the higher order modes can be so lossy that simply die out, allowing oscillation on only TM00 mode and even for a wide aperture fiber. Power scaling in the operation of a fiber laser is therefore possible without compromising the spatial quality of its emission. So by bending, choosing the sharpness of the bending, we can do that. Now we'll discuss fiber amplifier, basically. As I have mentioned that fiber amplifier will not have the cavity, otherwise almost same of the fiber laser. So basically similar to any optical Basically, similar to any optical amplifier, an active fiber can also amplify light of frequency that falls within its gain bandwidth. In case of EBM doped fiber amplifier, EBM has a strong absorption at 980 nanometer wavelength. The 980 nanometer photons from the diode laser excite. So here, excite the EBM ions to a higher energy state from where they drop down to the metastable state and get stuck there, and in turn gains builds up across 1520 to 1570 nanometer region of wavelength. So this is the diode pump. The input is weak for 1550 nanometer. So if a diode pump is injected, so they got absorbed and from this excited state non-radiatively decay down to the metastable state, which is 10 millisecond lifetime compared to here, this is 1 microsecond. And from this metastable state, they stuck there, and in turn the gain builds. And these photons of 1550 nanometer wavelength will induce simulated emission in this excited species in the metastable state. This will cause burning of the gain, resulting in the amplification of the input signal. So they will increase the gain. The ability of EDF to amplify, which is EBM doped fiber EDF light at 1550 nanometer, where glass fibers are practically lossless. They has been used in optical communication. And for fiber laser, this metastable state has lifetime of 1 millisecond. Now we'll go into semiconductor laser. certain material behave like a semiconductor is believed to have been first scientifically documented in the work of British scientist. He discovered in 1833 that the resistance of a silver sulfide decreased with increasing temperature in a complete contrast to the behavior of metals. With metals, the resistivity increases with temperature. These semiconductor materials behave much like an insulator at lower temperature but conduct electricity like metals at room or elevated temperature. They are insulators at room temperature or elevated temperature. They behave like a conductor. So in 1833, we got the semiconductor, but it needed almost a century to build first PN junction. So when the PN junction are biased, they behave like a diode and is regarded as the very first semiconductor electronic device. The transistor, a variant of a PN junction that brought a revolution in electronics and fetched 1958 Nobel Prize. For transistor PNP or NPN configuration. That is why it's called a variant of PN junction. And those who got the Nobel Prize for inventing a transistor in 1948, one of them also got a Nobel Prize, and he became the only person to date to get the Physics Nobel Prize twice, which is John Bredin. He developed the BCS theory also for conventional superconductivity. So LED comes at a very later stage. In 1962, Michalniak get first LED by generating spontaneous red light from forward biased PN junction. And this leads to build a semiconductor diode laser later. The race to build the diode laser was too intense that almost simultaneously the groups working at the MIT Lincoln Laboratory in Massachusetts and IBM Center also reported lasing from gallium arsenide diode. And 1963, Soviet Union also developed the diode. Inbuilt tiny size of the semiconductor laser, enabling its ready integration with other devices primarily led to an explosion of research activity across the world to prefer the diode laser technology by exploiting the unique properties that semiconductor is known to offer. This has led to the emergence of diode lasers as the undisputed leader in the world of lasers. As a matter of fact, to say that today dark lasers have made profound impact on our day-to-day life. It's a overstatement. They are present everywhere. The CD players, the DVD players, the barcode laser, all are semiconductor lasers. So, before we go into the semiconductor lasers, we should know about the basics of semiconductor physics. Some of you may know that, but again, for the sake of complexity of the course, So basically, when electrons revolving around the positive charge nucleus in any atom. So, but when we take two atoms, we consider here two hydrogen atoms, two isolated atoms, and they are at a distance of r, which is more than 2 r naught. Their wave function doesn't overlap. So see here the intermolecular distance. When they are at least r2 naught, they actually one energy level. Two atoms, four atoms, and n atoms. Whatever is the case, there is no appreciable overlap of the two atoms, and consequently, the discrete ground energy levels remain the same as of that of an isolated atom. So, for isolated atoms, the discrete constant energy level remains the same. However, as r approaches to r naught, the function begins to overlap, and each electron orbit around both nuclei. So, for these two will overlap, and for two atoms there is two. For four atoms there are four wave function overlapping. For n atoms the overlapping will be like that. So they clearly form a band, and the wave function will use as the combination of the wave function isolated atoms with both the same and opposite sign. The situation is represented like this. So here that see both the wave function is isolated, and when this combination is symmetric, like wave function of each electron can be approximated as a combination of the wave function of the isolated atoms with both and the same and opposite sign. When the two atoms is the same sign, the combined wave function will be like this, and when the wave function has opposite signs, the combined wave function will be like this. So two wave function essentially correspond to two different energy values. This is equivalent to saying that when the two hydrogen atoms are close enough, the ground state energy level splits into two. So basically, when two hydrogen atoms are closed, ground state energy levels splits into two. When there is a 4 level, then the ground state energy level splits into 4 generally n atoms. The splitting will be n. In a solid, an exceptionally large number of atoms are packed in a tiny volume, and then consequently the levels come to so close to each other that they essentially form an energy band. Form a band. So there is like formation of energy band is possible primarily for the valence electrons that are relatively loosely bound to the nucleus to be as they reside in the outermost shell. The wave function of the inner electrons belonging to different atoms forming a solid exhibit very little overlap. We know that the shells are denoted by the principal quantum number n. It may be noted that a shell with the principal quantum number n has an equal number of subshells denoted by orbital number l. So, n principal quantum number, then orbital quantum number l that vary from 0, 1, 2 to n minus 1. The maximum number of electrons that can reside in the subcellular orbital quantum number is 2 to L plus 1 max number of electrons. The subshells with 0 is basically is S, this P, this D, then F, then G, and etc. So S can have 2 electrons, P can have 6 electrons, D can have 10 electrons, and F 14 electrons. So in order to know that how the formation of energy band by the valence electrons on a conductivity of a solid, we consider a typical case of a sodium atom. So this is the sodium atom. So sodium atom has 11 electrons. So basically this distribution would be for the quantum number would be 1 and 2. For 1, that is only S. So because L varies from 0 to n minus 1. For 1, 0 is 0, so 1 is. For 2, 2 is 2p. So this is 2, this is 2. This is 6, that consists 10. Then the next quantum number, obviously that would not be in D because they behave like this. 3 is 3p, 3d. So here next quantum number would be 3s because for 2 we can go up to s and p. So that will be 1 here. And anyway, it goes like this. 1 is 2s, then 2p and 3s, then 3p, then it will follow 4s, then come 3d. Not after 3p that comes 3d. That you need to understand when you like go for the electron distribution. So only one electron resides in 3s while the occupancy of the s subshell is 2. Thus this electron is called valence electron. When sodium atoms get closer to form a solid, the 3s energy level will be broadened to form an energy level. If n atoms have joined together to form a 3 atoms joined to form a solid, this 3s band, then it can have a total of 2n electrons. Can have 2n electrons. Only n electrons resides in 3s band. It is therefore only half filled by the electrons. The inner levels are fulfilled and very close to the nucleus. The situation is like this. So this 2n will be half filled only because 3s was already half filled. When a modest potential difference is applied across a block of sodium solid sodium, the 3s band electrons can readily acquire energy while still remaining in the same band. The ensuing drift of these valence electrons therefore constitute a net electric current. It is no wonder that the sodium is a good conductor of electricity and accordingly classified as a metal. In case of an insulator, their valence band is fully occupied, and the valence energy band here is thus fully occupied. The next outer subshell that is completely empty, that has the potential to function as a conduction band, is separated by the valence band by a forbidden energy gap, that is some electron volts. The average thermal energy under ambient condition being only 0.025 electron volt, the valence electrons are unable. This is for metal, this is insulator. So they cannot breach that gap and go to the conduction band. This barrier cannot be reached by applying an electric field. Here then comes semiconductor. Semiconductor is like this. For semiconductor, the distance between the fully occupied valence band and conduction band is very less. So that's why when you material also behaves like an insulator and low temperature, this band is almost 1 electron volt. For insulator, that is many electron volts actually. So if you in a higher temperature, some of the electrons go to the empty conduction band and they start conducting. So that create a pair of conductors, that is electron and hole. The holes can be regarded as a deficit of electron or as a positive charge. Just as the motion of the electrons in the conduction band results in the flow of the current, the flow of current in the valence band too arises from the motion of holes. In reality, holes do not move on themselves. So when an electron moves, the hole automatically moves. So if this electron goes from here to here, the hole moves from in the opposite direction. The electron, if moving in this direction, hole moves in the opposite direction. So following the creation of a hole in the valence band, so here the valence band, a hole has been created. So here a hole has been created. So electron moves to fill the gap, thereby creating a hole in its original location. As the second electron now moves to fill a new hole, the second electron now moves to a new hole. Then another hole is created, and the hole is moving. So in a semiconductor, the flow of current in the valence band can as well be thought of originating from the motion of a hole instead of the electrons. This hole-centric approach is also inherently simple to analyze in the valence band. There are fewer holes that are greatly outnumbered by the electrons. So for now, that is the basics of semiconductor physics that has been discussed in the class. Now we will go to the quiz questions of the previous year. First question. volume ratio, efficiency, fiber lengths were not possible. Right one way. We needed to go for an end-to-end counting. We had to wait for the junction diodes to invent to be invented. So I should say. Question number two is a coiled slazing. Action effect. Three. There is no loss energy due to refraction. Light can take carved path. So as we know that in fiber there is no interference and reflection effect. Fiber basically works with the new loss of energy for refraction. And as the coil fiber, there is no that much of the loss of energy due to coiling or the bending. Like in coil, if there is not any bending, there is no energy loss. So this is the correct answer. third question is the fiber laser resurfaced with the birth of semiconductor laser because one, laser beam size exceeded fiber cross section. Second, optical pumping of fiber was possible with the emission of semiconductor laser. Third, both side and end pumping possible. Four, all of the above. So basically, we know that fiber laser enable is because it has a narrow emission cross section and it easily can be coupled with the fiber. So this is the answer. Fiber laser beam size does not exceed fiber cross section. Question number 4. In case of optical fiber of refractive index mu1 and mu2, the optical fiber of refractive mu1 surrounded by a medium of refractive index mu2, the critical angle is, we know that mu1 sine theta c, mu2 sine 90 degree. So this is mu1, this is mu2. For critical angle, that angle is 90 degree. So 90 degree is 1, sine 90 degree is 1. The mu1 theta c would be sine inverse mu2 by mu1. That is the answer. Question number 5. A fiber is necessarily cladded one for mechanical strength, two to prevent spillage of light through refraction. Three, to enable light to enter the fiber. 4, to ensure total reflection. So the thing is, for total internal reflection and the enable to light the fiber, we don't need any cladding. The core is enough. The air is anyway the rarer medium. Need denser to rare interface, and air is obviously rarer than the core. We basically need to protect the core. We cannot afford any scratch on the core and the support the structure. So that is why, to give only the mechanical strength, we introduce cladding in the fiber. The refractive index of clad mu1 and fiber mu2 are related in the following manner. 1 mu1 is equal to mu2, 2 mu1 is greater than mu2, 3 mu1 is less than mu2, 4 mu1 is greater than mu2. So we need denser to rarer medium. So basically mu1 has to be less than mu2. That is the answer. Question 7. The incident beam will undergo total internal reflection. Reflection, if we know the answer, is angle of incidence is greater than critical angle. Question number 8. Fiber lasers can be efficiently pumped by LEDs, diode lasers, flash lamp, solid state lasers. We have already discussed that only diode, after the invention of diode laser, fiber lasers has been seen its proper glory. So only the diode lasers can couple the light in a pumping mode efficiently for the fiber lasers. Lasing medium in a fiber laser is fiberglass. That's not true. Clad medium, that is also not true. Clad is there for the mechanical strength. Dopants in the fiberglass, that is the actually glazing medium. Earth 4 is none of the above. So that is the answer. Question 10 is, the fiber laser emission is generally SLM or multi-transverse mode. Second is SLM TM00 mode. Third is multi-longitudinal, multi-transverse mode. Fourth is multi-longitudinal renal, TM00 mode. So it is basically longitudinal and TM00 mode. It is neither SLM, and TM00 is the basically mode. And for when we for better efficiency, we increase the radius or the diameter of the core, that becomes multi-longitudinal. But those multi-longitudinal will have very small spatial quantity in that fiber laser emission. So that is for today. See you in the next class.